Welcome back to Electrons Dance. Today I want to talk about pendulums, and I'll touch a little bit on physics, mathematics, and electronics. Oh, and maybe a little history too. As far as we know now, back in the 1600s, Galileo was first to notice how useful a pendulum might be for timekeeping, because its period was seemingly constant once the length was fixed, regardless of its mass or even how far it swung side to side. Like so many things encountered during my K-12 education, this topic was presented early on as a simple one, wrapped up in a bow, consisting of a nice, neat formula. At least what I remember from junior high and high school was being told that the period of a simple pendulum swinging back and forth in Earth's gravity is 2 pi square roots of L over G. Period. Paragraph. End of story. A clean, elegant equation like that usually makes a strong impression on the student, and in fact it goes a long way toward making us think the underlying analysis is just as clean and elegant. Naturally, I didn't think much more about pendulums for several years. Then in college, with tools like calculus and free body diagrams and such at my disposal, I was expected to start figuring out things like this for myself. Lo and behold, the simple pendulum re-entered my consciousness in the form of an exercise. It turns out the equation at the root of this thing's behavior is not trivial. So here we have a free body diagram of it, frozen in time at some arbitrary point during its swing. Gravity pulls straight down on the mass m with a force of mg, g being the acceleration due to gravity. Pretty dang close to the same at ground level whether you're in Alabama or Italy. The rod or cord or whatever it is attaching the mass to some fixed structure is tilted at some angle theta away from vertical. The downward force of gravity can be broken down into 2 components, one aligned with the cord and one at a right angle to that, back toward the vertical. All the cord can do is pull back along its length, and so it does, exactly balancing the lengthwise component of weight. The right angle component is unopposed, so it accelerates the mass back along the tangent of the arc, diminishing theta. The magnitude of that instantaneous acceleration is mg sine theta over m, or just g sine theta. At least we can already see why the mass doesn't change the result, and of course we're neglecting friction here. Translating that linear acceleration into rotational terms, the angular acceleration along that arc of radius L is linear acceleration over radius, or g sine theta over L. So, using the dot notation for time derivatives popular in dynamics, that angular acceleration, the second derivative of the angle, is theta double dot equals minus g sine theta over L. And that minus sign is just because, as I said before, that downward force is acting on the mass in the direction to diminish theta. Now, what the heck are we supposed to do with the sine theta in that equation? Understand, the problem isn't the mere presence of a sine function here. We know how to integrate that. The problem is we have to integrate over time, not over the angle theta. And theta as a function of time is exactly what we don't know. I, for one, do not know how to integrate an unknown function. Of course, we've been introduced to the idea of infinite series, and we could rewrite sine theta as a sum of powers of theta, starting with some constant, plus various coefficients times powers of theta, theta squared, theta cubed, to the 4th power, etc. ad infinitum. We could then integrate those terms in general form and add up the results until we got as close as we like or run out of steam. So where does that nice, neat equation come from? Well, if we assume the sweep of theta is small, we can quite reasonably use the small angle approximation. Substituting theta in radians for sine theta, and our equation becomes theta double dot equals minus g theta over L, which is pretty easy to solve. Taking a shortcut through the frequency domain, as we electrical engineering types are apt to do, we can do a Laplace transformation on both sides of the equation and rearrange terms to get s squared theta plus g over L theta equals 0. Without worrying about initial conditions, the system behavior depends on the roots of that equation, which are purely imaginary. S equals plus or minus j square roots of g over L. Okay, j is I for you math types, the square root of minus 1. But for us electrical engineering types, I is current, so we use j for the imaginary number. So the frequency of oscillation in radians per second is omega equals square root of g over L. In more familiar terms, omega is 2 pi times f, 2 pi times the frequency, which is square root of g over L. And so the period is 1 over that, or t equals 2 pi square roots of L over g. Et voila. Okay, but how close is that to the solution of the actual equation? Turns out it's pretty close until the initial value of theta gets pretty big, like maybe 30 degrees or so. Remember, I said we could rewrite as an infinite series and integrate, calculate a bunch of terms, and get as good an approximation as we like. Folks with more patience than me have done that. To quote Sears and Zemansky's university physics, when the initial angle is less than 15 degrees, the true period differs from that given by the approximate equation by less than 0.5%. When you're faced with something like this that you can't express in a nice, neat equation, whether or not you can find something tedious like an infinite series, or worse still, a continued fraction, you can always turn to numerical methods. One such method here is a computer simulation of the physical system, with the answer you really need extracted from that. As a freshman engineering student, that's the kind of thing I did for fun. Fortunately, even a geek like me could get a date now and then. I recreated that experience just now, writing a simple Pascal program to run a simulation based on the exact equation. You can get a lot more sophisticated about it, but the idea here is just to slice time up into tiny steps. Start at the initial conditions, calculate the acceleration at each instant, update the velocity from that, update the position from that, then go to the next time slice and do it again. If all you want to know is the period, just have the program check for 0 crossings going a certain way and count time between them. Here's a sample run in progress, and I'll put the source code in the notes. Let me also make a graph of the period versus the starting angle and include that in the video. Now, for a down-to-earth reality check, you can make actual measurements in a physical system. In this case, I made a 2-meter-long pendulum with a small weight at the free end, hung it in my office doorway, and made an electronic contraption to measure the period with about 1 millisecond resolution. Here I am using an infrared beam to sense the vertical crossings to keep from disturbing the pendulum. I have some Raspberry Pi Pico boards lying around, so I'm using one of those to read the sensor input and measure the period between every second crossing. You know, back and forth, back and forth. A laptop computer provides both power and communication over a USB port. The MicroPython program running on the Pico sends the measurements to the laptop as plain text. And a terminal program on the laptop captures the data. I'll put that source in the notes too. Since this is a real system, complete with some degree of friction, mainly in the form of drag in the air, the pendulum eventually slows down and stops. Unlike the tidy behavior you might expect from the simplified equation, the period of the real pendulum changes as it slows down, reflecting the true period, which is a function of the changing amplitude. So let's see how these different ways of looking at the same problem agree with one another. Starting with the simplified equation, the acceleration due to gravity here in my office should be pretty close to the standard value for Earth's surface, 9.81 meters per second squared. I'm not going to dive into the smaller digits on that. The length of the pendulum in the doorway there was pretty close to 2 meters even. That gives us a calculated nominal period with the simplified equation of 2.837 seconds. Okay, I'm not going to add up a bunch of terms from that infinite series right now. So for our theoretical model of the period from the exact equation, let's just use my computer simulation results. Those are shown here in the graph. You can see that we start out a little bit higher than the nominal value at 30 degrees from vertical as our starting position. But then as that starting position, or equivalently amplitude, gets smaller and smaller, we get closer and closer to the simple version, to that nominal value. Okay, what about our physical measurements? You can expect some slight errors here. The largest source of error I can think of is my measurement of the length of the pendulum from the pivot point to the center of mass of my weight. I measured that with a tape measure, so that's going to be off a little bit. Still, my measured period at small angles is pretty close to the calculated value. Started a little over because I released the pendulum from an initial angle somewhere around 25 or 30 degrees. And you can see that as the amplitude decreases, that measured period is dropping fairly quickly at first, and then leveling off pretty close to the nominal value. It's always a good idea to cross-check your answers when you can. Well, that's it for now. So go find something more fun to do. Just don't forget to come back.